For decades, most cosmologists have told the same story. The universe began with a primordial blast, the Big Bang. It's a tidy narrative, dramatic and easy to repeat. Roger Penrose thinks it leaves far too much in the shadows. Penrose has never been impressed by answers that settle too quickly. When the Big Bang is treated as an absolute origin, he hears a way of stepping around the hardest questions. This is no act of rebellion for its own sake. He points to a deeper reason. The equations don't close cleanly, and the paradoxes multiply the moment you press them. He keeps returning to a simple point. The real puzzle isn't only how the universe began. It's what we even mean by a beginning. A true beginning, in the standard picture, demands an extraordinarily special condition, a singularity with unique properties. Yet singularities appear elsewhere in physics, most famously inside black holes, and the character is different. Penrose finds that contrast hard to swallow. One set of rules seems to be doing one thing in one place, then behaving very differently in another, while everyone carries on as if the word singularity explains it all. What bothers him almost as much is the confidence with which many people accept the standard fixes without revisiting the foundations. Take inflation, the popular patch meant to explain why the early universe looks so smooth and uniform. Penrose finds it troubling because it quietly brings in an asymmetry. He asks, with dry skepticism, why it would work in one direction and fail in the other. If physics aims for coherence, it shouldn't lean on one-way rules while describing something universal. For him, inflation doesn't touch the deepest issue. It doesn't explain why the universe had such an astonishingly special past in the first place. Penrose can be blunt about it. "I don't believe a word," he says, without much patience for polite hedging. That is where the break begins. Penrose proposes that the Big Bang wasn't the beginning of everything. It was a chapter inside a much larger cosmic story. He doesn't frame that as a hunch. He frames it as a response to what the conventional theories leave hanging and to what they quietly gloss over. Science moves forward when someone is willing to risk an idea that sounds outrageous. Penrose even admits how it comes across. "My idea is crazy," he says. Then he adds, almost immediately, that a crazy idea is exactly what you need when the conventional ones aren't working. And with that, the ground shifts. Reality, in Penrose's view, keeps refusing to fit the mold we've built to contain it. Roger Penrose puts forward an idea that reshapes how we think about time and the universe. In his view, the cosmos never had a single true starting point. It belongs to an endless sequence of cosmic cycles he calls Aeons. Each Aeon begins with its own Big Bang and runs on towards a future so remote that matter, time, and scale stop behaving in the way our everyday intuition expects. Penrose calls this framework conformal cyclic cosmology, shortened to CCC. The storyline begins with something familiar: expansion. Over unimaginably long stretches, the universe keeps thinning out. Matter breaks down, energy spreads, and what once looked permanent becomes fragile. The crucial step, in Penrose's picture, is the fading role of mass. In the far future, the particles associated with mass effectively lose that mass, and what remains is radiation, light-like content with no rest mass. With that, the usual anchors of physics begin to slip. Clocks and rulers rely on mass to define fixed scales. Remove mass, and the question "how big is it?" becomes harder to even phrase, because scale has no firm physical foothold. That is where Penrose makes his most surprising claim. The far future of one Aeon can connect mathematically with the Big Bang of the next. What looks like an absolute ending from our perspective, becomes the threshold of another beginning. The handover is neither dramatic nor noisy. It's a change of description, a way of relating one cosmic era to the next when scale no longer has a privileged meaning. The bridge depends on conformal geometry. Conformal geometry tracks shape and proportion while allowing absolute size to fade into the background. When mass disappears, absolute scale stops functioning as a physical idea, and conformal geometry becomes the natural language for what remains of space-time. Penrose reaches for a visual comparison to make that feel less abstract. He points to Escher's drawings, where figures, angels and demons, for instance, repeat all the way to the border, compressing something that feels infinite into a finite frame. In image 1, that metaphor matters. It captures how the structure can persist even when the notion of bigger and smaller loses its grip. Penrose also nods to the spirit of Dirac, Einstein and Planck. He isn't trying to throw away classical physics. He's trying to read it with more nerve. The continuity he's after rests on the geometry of space-time itself. Mass defines scale. Without it, absolute magnitudes fall away, yet ratios and relationships remain. So at the end of an aeon, the universe, stripped of structure and mass, becomes a scale-free template. In Penrose's telling, that template can be expressed as the starting point of the next aeon, without requiring the usual picture of a violent reset or a classical singularity carrying all the explanatory weight. Penrose insists this is grounded in known laws pushed to their limits. A massless universe doesn't turn into nothing. It leaves behind a structure without scale, and that structure can seed a new cycle. This is also where his dissatisfaction with standard cosmology shows. Inflation, widely accepted, adds a burst of rapid expansion near the beginning to explain why the universe looks so smooth and uniform. Penrose finds that move unsatisfying. It leaves the deeper question intact: why the universe had such a remarkably special past. In CCC, that smoothness can be inherited because the previous aeon could have ended in an extremely uniform state. The beginning becomes a gentle handover between cycles. One of the deepest problems in physics isn't hiding in the equations. It lives in what many people decide not to examine. Roger Penrose has spent decades pointing to a crack at the heart of quantum mechanics: the collapse of the wave function. Collapse is the moment a particle stops being described as several possible states at once and becomes one definite outcome. Quantum theory describes the spread of possibilities with extraordinary precision. Daily reality gives us single facts. Penrose keeps pressing the awkward questions. What triggers the shift? When does it happen? What settles the result? Traditional answers often skirt the issue. Some say measurement causes collapse, observation forces a definite outcome. Others claim collapse never happens, and every possibility continues in parallel universes. Penrose rejects both. In his view, they function as ways of walking around the problem rather than explaining it. He puts it sharply: physics is ignoring one of its biggest problems. It gets ignored partly because taking it seriously would mean questioning the foundations. Penrose insists collapse belongs to the world itself, not to our descriptions of knowledge. If possibilities turn into facts, something physical is doing that work. That process deserves the same seriousness we bring to gravity or thermodynamics. To make the point bite, Penrose compares two extremes of the universe: the Big Bang and the singularities associated with black holes. Both mark places where our familiar laws fail, yet they are not equivalent. In a black hole, space-time can become extremely curved in one direction, while other directions remain comparatively well-behaved. In the Big Bang picture, the collapse is more radical. The entire spatial structure collapses together, down to a point with no ordinary sense of scale, form, or direction. This distinction matters when you look at what general relativity suggests near a singularity. In the 1970s, Belinsky, Lifshitz, and Kalatnikov developed what's known as the BKL model. It describes space-time near a singularity as geometrically chaotic, directions stretching and collapsing in a wild, irregular way without a stable pattern. Charles Misner also explored this territory within general relativity, studying how violent and complicated the dynamics can become as such an extreme is approached. Penrose draws a clue from these models. Singularities are not all the same. If the universe began in a singular state, one might expect something closer to the BKL behavior. Jagged, turbulent, disorderly. Yet the Big Bang, as inferred from the cosmos we observe, looks unusually smooth and uniform. Penrose treats that as an exceptional condition, a special past. Why would the universe start in such an ordered state? For him, the collapse problem returns here with force. The Big Bang was more than a burst of energy. It was a highly organized starting point. That early order may connect to whatever process makes a quantum state settle into one concrete reality. The universe emerged from a precise condition, and that precision remains hard to explain, while the question of how reality selects one outcome among many is left unresolved. Penrose knows why this makes people uneasy. A genuine physical mechanism behind collapse suggests quantum theory is incomplete, and revisiting a framework that has worked for almost a century is not comfortable. Yet Penrose thinks science advances through that discomfort. It moves forward by confronting what refuses to fit. In the heart of the universe, he sees a mystery still waiting, and it won't disappear just because we stop looking. Sometimes the deepest ideas arrive in ordinary moments. Roger Penrose remembers one of his with unusual clarity. He was walking through London, outside Bedford College, when something simply clicked. It was 1964. A sudden intuition crossed his mind, and it led to what became the trapped surface theorem. Penrose saw that, under certain conditions, gravitational collapse cannot be stopped. If a region of space contains a surface where every ray of light, even light trying to escape, ends up falling inward, then a singularity must form. General relativity forces the conclusion. It was a rigorous step. Singularities were not harmless quirks of mathematics. They were physically unavoidable consequences. The result did not cause instant uproar at the time, yet it became part of the foundation for the theorems Penrose later developed with Stephen Hawking. That work shaped how modern physics thinks about black holes and cosmic collapse. Penrose treats that day as more than technical progress. It also became a lesson about understanding itself. There was no blackboard performance, no long chain of calculations. It was a moment of clarity, sudden and quiet. After that, Penrose began asking what understanding really means and why it feels different from following procedures. He also admits there is one topic where people misread him more than anywhere else: consciousness. He calls it murky ground, and he has said that sometimes he thinks he should never have got involved. Still, he did, and that path pushed him towards an unsettling thought. Understanding is not the same thing as calculation. Years later, while studying Gödel's incompleteness theorems, Penrose found a disturbing parallel. Gödel showed that any sufficiently rich formal system contains true statements that cannot be proved from within the system itself. The rules cannot reach them, even when the statements are true. Yet a human being can sometimes see the truth from outside the system. From this, Penrose draws a provocative conclusion. Computation has limits that the mind appears able to cross. A computer can execute rules flawlessly. Yet rule following is different from grasping why something is true. He captures the flavor of the problem with a self-referential sentence. This sentence is not provable. If the system is consistent, the sentence cannot be proved inside it. From outside, you can see the trap and recognize the point. The mind seems able to stand beyond formal boundaries and judge what the system cannot settle. Penrose links this to a tradition he respects. Dirac, one of the most influential physicists of the 20th century, distinguished between mathematical beauty and genuine understanding. Penrose echoes that view. He suspects something about mind resists clean coding. If human understanding is not computable, then consciousness will not be computable either. The brain cannot be reduced to a machine that simply runs rules. From that walk in London to Gödel, Penrose keeps crossing the border between physics, logic, and mind. And he ends up with the same thought. Understanding is a way of seeing what is otherwise invisible. Science moves forward when it dares to look there. The key to the universe may sit inside a question that still refuses to settle. Is quantum reality only a mathematical convenience or a concrete physical structure? Roger Penrose treats it as something real and active in the world. He thinks the way that reality collapses may point towards the origin of consciousness itself. Quantum physics is one of the most successful theories we have. It predicts the behavior of atoms and particles with extraordinary accuracy. Yet it leaves a central mystery untouched. What truly happens in a quantum superposition? People say an electron can be in two places at once, or that a glass on the edge of a table has not decided which way it will fall. Penrose insists this is not colorful language. It is what the wave function, the core mathematics of the theory, describes. Daily experience looks different. We see one outcome, not a blend. The moment of decision is the puzzle. What forces the world to stop hovering between possibilities? What ends the superposition and delivers one definite result? Penrose has little patience for answers that lean on observation or that treat collapse as pure chance. He argues for a physical cause, an objective event. For him, superposition is the world trembling between multiple possible futures. Here comes his radical move. Gravity plays the deciding role. Picture an object in superposition. It sits in two places at once, which implies two different curvatures of space-time at the same time. Penrose's point is blunt. Space-time cannot hold incompatible geometries indefinitely. Once the difference between those curvatures passes a threshold, the system snaps to one outcome. In this account, collapse does not wait for an external measurement. It happens spontaneously, driven by the structure of the universe itself. The larger the mass involved, the larger the space-time distortion, and the faster the collapse. Small quantum systems can remain delicately suspended. Larger ones cannot sustain the ambiguity for long. Penrose developed this proposal with the anaesthetist Stuart Hameroff. Together they offered a model called Orch-OR, short for Orchestrated Objective Reduction. In that picture, certain quantum processes occur inside the brain and may contribute to consciousness. Penrose treats it as a physical hypothesis. If collapse is real and gravity helps drive it, then the brain may be a place where it matters. The proposal is stark. Conscious experience arises when a quantum superposition in the brain collapses through a gravitational effect. In that instant, a subjective moment appears. Penrose draws a hard line around computation. This is not a theory about information processing. He argues that consciousness is not computable. Algorithms cannot reproduce it, and artificial intelligence cannot simulate it into existence because the crucial ingredient is a physical event that formal systems cannot capture. He invokes Gödel. In any sufficiently rich system, there are truths the system cannot prove from within itself, yet a mind can recognize them. Penrose sees an echo of that limit in physics. Certain processes resist reduction to computation, and those processes may sit at the root of conscious experience. If Penrose is right, consciousness is neither a glitch nor an illusion. It becomes part of quantum reality itself, woven into how the universe turns possibilities into facts. When you raise your arm or decide to blink, it feels like a conscious choice, yet the experiments point somewhere else. In the 1980s, Benjamin Libet placed electrodes on the brains of volunteers and found something unsettling. The brain began preparing the action before the person reported any feeling of having decided. That finding puts pressure on our idea of the present. What we experience as now is rarely a clean window onto the instant. It is the outcome of neural processes that have already happened. Our sense of the present is a reconstruction, a kind of temporal assembly that arranges recent events as if they were immediate. In everyday terms, it's a little like watching a live broadcast with a slight delay. You feel present, yet the feed has already been processed, buffered, and assembled. Libet's results suggest something similar in the mind. The now you experience may arrive a fraction late, already shaped into a coherent story. Roger Penrose treats Libet's result as more than a curiosity. He uses it as a window into something deeper, what consciousness is and how it relates to time. From a classical point of view, think of the Hodgkin and Huxley model. Neurons act through electrical and chemical signals, following a clear chain of cause and effect. That machinery can describe how signals travel and how decisions become actions. It does not, by itself, explain why there is a conscious experience tied to the outcome. Why do we feel time as continuous? How does a subjective stream of moments arise from brain processes that are in many ways broken into fragments? Penrose suggests the key may lie in tiny structures inside neurons, microtubules. These fibers, present in the brain's pyramidal cells, were long treated as mere scaffolding. Stuart Hameroff, an anesthetist who worked with Penrose, argued that microtubules might do more. He suggested they could support quantum-like behavior, even maintaining states of superposition. If that is true, each conscious moment might be linked to a quantum collapse inside microtubules, and that collapse would not necessarily follow the familiar arrow of time in the way classical processes do. Consciousness might be organizing the recent past into a subjective present, stitching experience together from within. That would also help make sense of Libet's timing. The brain acts before we think we decide because consciousness is not simply reacting to events as they arrive. It is rearranging them, building the feeling of continuity after the fact. Penrose adds one more possibility. This internal clock may be using processes that do not obey linear time, but a different logic that conventional physics has not yet captured. In that view, consciousness is more than perception. It is integration, reordering, and a kind of quantum synchrony. If time seems broken inside our heads, as neuroscience suggests, it is not because the brain is failing. It may be operating within a dimension of time we do not yet understand. And understanding that dimension, Penrose thinks, could be the next major step in a physics of mind. In theoretical physics, names carry weight. Hawking, Witten, Wheeler, Dirac, Feynman. Towering figures who helped set the direction of modern thought. Yet Roger Penrose does not treat authority as an argument. He treats ideas as arguments. When he disagrees, he says so, even when the room is full of legends. He speaks with a kind of clipped honesty. Colleagues may wince, yet he prefers a clear objection to a polite fog. For decades, Penrose has held positions that make the consensus uncomfortable. Where many people see an unresolvable paradox, he often sees a problem that has been framed badly. The clearest example is the debate over information loss in black holes. For a large part of the physics community, it counts as one of the deepest problems in modern theory. Penrose is blunt. It's not a paradox, it's stupid. His objection is not theatre. He thinks the very demand is misguided. The idea that a black hole must preserve information as though it were a cosmic computer, keeping perfect records of everything that fell in, strikes him as the wrong way to think about nature. A black hole can evaporate without the universe having to keep every detail as retrievable data. Physics can accept loss, provided it understands what is lost and how. His disagreements do not stop there. At the well-known conference in 1988, when Edward Witten proposed his negative constant as a basis for string theory, Penrose responded with mathematical coolness. That makes no sense. In Penrose's view, the proposal might look elegant algebraically, yet it had no real geometric footing. It did not correspond to any structure you could expect to find in the world. That is the heart of his criticism. Penrose has always defended a geometric vision of the universe. Curves, spaces, and structures you can picture. Not only symbols you can manipulate. His twistor program, for example, begins from a visual intuition about space-time, set against what he sees as the extreme abstraction of string theory. He has also questioned the blind trust placed in simulations and computation, especially when the subject is consciousness. Artificial intelligence, he says, is not consciousness. The issue is not a shortage of computing power. The issue is that something essential is missing, a physical process that is not computable. For Penrose, the belief that an algorithm could simply become conscious shows a misunderstanding of what consciousness is. Even figures like Eugene Wigner, who argued that mind must play a role in quantum physics, have often been ignored or misread. Penrose returns to that territory, yet he does not present it as a philosophical preference. He treats it as a physical necessity, tied to the unfinished business at the core of quantum theory. In Penrose's view, science needs the courage to move beyond fashions, beyond consensus, beyond untouchable reputations. Physics is not a practice of reverence, it is a practice of understanding. And understanding sometimes means saying what nobody wants to hear. This journey ends where science perhaps ought to begin, in doubt. Not the shallow doubt that performs skepticism, but the kind that forces you to look past what has been accepted. If Penrose teaches anything, it is that even among giants, clarity does not come from noise. It comes from the willingness to think differently. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.